Hello everyone, my name is Ricky and I'll be presenting my thesis topic, Beamforming Performance of a Standalone Digital Piezoelectric MEMS Microphone Array, which has been completed under the supervision of Professor Melinda Hodkiewicz and Dr. Ben Travaglioni. Condition monitoring involves tracking equipment parameters in operation to inform the health of machinery. Any significant deviations from expectations can then be used as an indicator of a developing fault. This information is used to optimize maintenance work by informing predictive maintenance to reduce unexpected downtime. It is a commonplace technique which is seen across many industries, especially the resources industry, which is particularly relevant to us in Western Australia. A common theme in condition monitoring is that the acquisition of equipment parameters requires sensors to be mounted on an equipment surface. Think vibration probes on a gearbox. What if we could perform condition monitoring remotely without the need for surface contact? Microphone arrays and beamforming open the door to this possibility. Microphone arrays are sound acquisition devices consisting of multiple microphones. Many today use micro-electromechanical system or MEMS microphones, which are micro-scale devices which convert mechanical elements into an electrical signal. They each record sound data which can then be subsequently processed using a signal processing technique known as beamforming. Beamforming enables the discrimination of a desired signal amidst interfering noise sources and the localization of a sound source relative to the microphone array. For example, when a compressor vibrates, it produces acoustic emissions, which the microphone array can then listen to amidst ambient noise. My work has been centered around this piece of technology, which we can see on the top left, the VM3000 MEMS microphone. It is a digital piezoelectric MEMS microphone, which was released in mid-2019 and is currently untested in literature. There are three characteristics which make this particular microphone so exciting. The first is its use of piezoelectric plates, which are implemented through 4 cantilever diaphragms. This is illustrated in the middle left figure, where we see these cantilever plates bend in response to incoming sound, and the stress generated by that bend produces a voltage proportional to the incoming sound waves. Capacitive MEMS microphones are the current dominant design in the market, and it contains a dual membrane design, which introduces susceptibility to failure from water, dust, and particle ingress as the membrane movement is inhibited. The second characteristic is that it is the only piezoelectric MEMS microphone which has been certified to an IP57 rating. It is dust protected and waterproof without the need for additional protective layers, meaning it is usable in harsh environmental conditions. The third characteristic is that it is a pulse density modulation digital output microphone. It has an onboard analog to digital converter, which removes the need for additional ADC hardware and enables these microphones to directly interface with commercial off-the-shelf hardware, such as Raspberry Pis. So this leads into the project scope for my work, namely to design, build, and assess the beamforming performance of a standalone digital microphone array with Wi-Fi connectivity using the VM3000 piezoelectric MEMS microphone. Note that this thesis has focused on creating a functional prototype array for testing in laboratory conditions and not an industrially applicable product. A custom designed PCB was required in developing the microphone array. For the array to be standalone, it needed to be wirelessly powered, portable, and remotely accessible. The Raspberry Pi 4 Model B was selected as the COTS solution to controlling the microphone array due to its size, weight, and high performance. It contains onboard Wi-Fi capabilities, meaning it can be remotely accessed, and it is capable of interfacing with a pair of VM3000 microphones. Note that this PCB was originally designed for the Pi 0W. However, due to interfacing issues, the Pi 4 was used instead. This will be discussed in the coming slides. On the right, we can see the schematic and layout of the PCB. The design accommodated for a single lithium phosphate 18650 battery cell to be used to power the Raspberry Pi, which would then in turn power the remaining electronics on the board. As the 18650 battery cell outputs 3.7 volts and the Raspberry Pi requires a 5-volt input, a TPS81256 boost converter was used to increase the input voltage to the Raspberry Pi from 3.7 volts to 5 volts. A 40-pin female header was built directly into the PCB itself, which enables any Raspberry Pi to be interfaced and swapped out when required. The inter-microphone distance has been designed to be 8.5 centimeters, which comes from a compromise between the maximal frequency measurable without aliasing, physical size of the PCB, as well as the flattest frequency response range of the VM3000 microphones. Here we see the final product of the microphone array prototype. We can see that a single 18650 cell sits nicely within the board, which runs through a switch and the TPS81256 boost converter to the Raspberry Pi header. The Pi 4 is sitting underneath the microphone array and is connected directly to the PCB via the GPIO connection header. We can also see that the VM3000 microphone pair sits at the bottom of the image. It should be noted that a single 18650 cell was sufficient to power the Pi0W, but was insufficient for powering the Wi-Fi module on the Pi 4. Therefore, during testing, the Pi 4 needed to be powered via cable. The first ancillary finding in this project is that although the Raspberry Pi datasheets state that the Pi contains a mode capable of interfacing with PDM elements, it does not provide clear instructions on how to enable this PDM mode. There was a clear lack of documentation regarding these instructions, which involved changing audio source code and replacing existing files. I have been able to develop this procedure to enable the PDM mode. This has been tested on both the Pi0W and Pi 4, and I've released these instructions online on the Raspberry Pi forums. In fact, someone has gone on to recently extend these instructions into an executable on GitHub. The second ancillary finding is that the Raspberry Pi 0W is incompatible with the VM3000 microphones. On the right, we see two ambient noise recordings. The top was recorded when the microphone array was interfaced with the Pi 0W, and the bottom when interfaced with the Pi 4. All audio recorded with the Pi 0W contained phantom noise characterized by an audible rhythmic ticking sound, which was present in the .wav files itself, as we can see from the distinct peaks. This phantom noise was not present when the Pi 4 was used when we contrast the top plot to the bottom plot. We suspect this phantom noise originates from the lack of hardware processing capacity on the Pi 0W. The Pi 0W is a single-core CPU device, meaning it must share processing power for the PDM data along with its other background processors, whereas the Pi 4 is a quad-core CPU device. The root cause, however, is yet to be determined and requires further investigation. The experiment setup for this work consists of two key stages, the data collection stage and the signal processing stage. A laptop running Jupyter Notebook was used to control a Keysight 33500B waveform generator, Raspberry Pi, and to process experimental data. The waveform generator was connected to a speaker, and the microphone array was placed 2 meters away along the same horizontal plane. A linear frequency sweep from 500 to 3000 Hz was outputted through the speaker and recorded by the microphone array. Starting perpendicular to the speaker, the array was then rotated 20 degrees about its midpoint and linear sweep repeated. This was repeated until a full 360-degree rotation was completed. Raw sound data was then processed using a simplistic time domain delay sum beamforming implementation on Python, which was developed by Dr. Ben Travaglioni. This implementation models theoretical beam patterns of a single perfect sound source and a single receiver in infinite space. This test was conducted once in the System Health Lab, which is a non-anechoic environment with plenty of surfaces for sound reflections to occur. Here we can see the microphone array is positioned perpendicularly to the speaker along the same plane, where the speaker is controlled using the waveform generator and the laptop. On the right, we see the angle guide, which was used to rotate the microphone array about 20-degree increments. This test was again conducted in the UWA anechoic chamber in order to compare the beamforming performance of the array under different acoustic environments. It should be noted that at time of testing, a wooden wall had been installed within the anechoic chamber, which presents a surface for sound reflections to occur. And to minimize the impact of those reflections, the array was positioned in the corner of the room. Here we see two sets of beam patterns generated at an array angle of 40 degrees and frequency of 1650 Hz. The beam pattern on the left is from the System Health Lab and the right is from the anechoic chamber. Let's first look at the graph on the left and break down what we're looking at. The graph contains two beam patterns, a theoretical beam pattern, which is in blue, and a real beam pattern, which is in cyan. The blue beam pattern is generated using idealized data, and the cyan beam pattern is generated using test data gathered by the microphone array. We are concerned with looking at two things to assess beamforming performance. One is whether the peak angles between the real and theoretical beam patterns align, and two is whether the shapes of the patterns are a strong match. We can clearly see that in the SHL beam pattern, a peak angle difference of 100.15 degrees exists, meaning the beamforming algorithm thinks that the sound source is coming from a location 100.15 degrees away from where theory would expect it to be. This is an example of poor beamforming. We can also see that at an angle of 0, the real beam pattern has a peak, whilst the theoretical beam pattern has a trough. This is caused as a result of the aliasing effects by sound reflections in the room, thereby causing inaccurate sound localization. If we were to compare this to the anechoic test data, we see that the angle difference has gone on from 100.15 degrees to only 10.29 degrees, and there is no longer visible aliasing within the beam pattern. These beam patterns are generated for every combination of array angle and frequency between 0 to 360 degrees and 500 to 3000 Hz. This slide shows us only a snapshot of the overall beamforming performance. Here, we have visualized the beamforming performance of the microphone array across all combinations of array angles and frequencies in a heat map. This heat map was generated by taking the normalized area difference between the real and theoretical beam pattern. A color closer to purple indicates an accurate beam pattern, and red indicates an inaccurate beam pattern. From a glance, we can immediately see that the heat map from the SHL lab data is riddled with red, orange, and yellow, indicating that the microphone array's beamforming performance is poor in non-anechoic environments. In the anechoic chamber heat map, however, we see a significant improvement in normalized beam patterns between real and theoretical patterns. The yellows and oranges become more apparent at frequencies above 2000 Hz due to aliasing, which is to be expected as the microphone array was designed for frequencies under 2000 Hz based on its inter-microphone distance. Therefore, we observe that the developed microphone array has a strong beamforming performance in anechoic environments, but performs poorly in non-anechoic environments. In recapping this presentation, I've demonstrated the successful design and build of a standalone microphone array utilizing the VM3000 Piezoelectric MEMS microphones. This array has been tested under two conditions, an anechoic environment and a non-anechoic environment, where it has exhibited strong beamforming performance and poor beamforming performance respectively. The beamforming accuracy in both cases is limited by the existence of surface reflections, hardware, and the complexity of the software beamforming algorithm used. Since the intended use case for this work is the resources industry, which is inherently very noisy, plenty of interfering sound sources and surface reflections exist. So future work on this project should be focused on developing the microphone array further to improve beamforming performance in non-anechoic environments. There are two key solutions to this known in literature. One is using more microphones, which improves the signal-to-noise ratio of the array, thereby allowing sound sources to be more accurately pinpointed. And two, using more complex frequency domain beamforming algorithms which is capable of better handling the impact of sound reflections. I'd like to give a special thank you to Melinda and Ben for their supervision and guidance throughout this project. Thank you for listening.